The most distant objects in the universe are also the most ancient. When we look at the Andromeda Galaxy, we're seeing it as it was 2.5 million years ago. Reflection of sunlight off of Jupiter takes 30 minutes to reach us, and even more nearby objects don't show up exactly as they are right now. The earliest light scientists have detected is from when the universe was just about a few 100,000 years old. This early light helped us discover the Big Bang. But what caused it in the first place? The universe could have been hibernating before something set it in motion. It may have collided with another universe, or perhaps it's part of an eternal cycle of cosmic bursts and rebounds. Why was the early universe invisible? How does energy define time? And why is 97% of the observable universe forever out of our reach? Could all of this lead to another Big Bang? Trying to understand the universe's origins, scientists use telescopes aimed at the furthest reaches of the cosmos. When these telescopes detect light from faraway galaxies, they're essentially capturing light that began its voyage countless eons ago. This is because light requires time to traverse space, and since the universe has been expanding from its birth, the journey of that light has also been stretched out. The limit of how far back in time we can see is determined by the distance light has been able to travel since the universe started expanding. The very first photons couldn't move freely, constantly being scattered off free electrons, which made the early universe opaque. When everything cooled about 380,000 years after the Big Bang, these primordial photons were set free and continued their journey in the direction they were moving at that moment. Over their long journey up until now, this light wavelength has stretched so much that it shifted from the visible spectrum to the microwave range, something researchers discovered when they detected what is called the cosmic microwave background radiation. Everything before this period of time is out of our observable reach, so scientists rely on projections to understand what might have occurred during the early stages of the universe. As time goes by, the overall entropy of the universe increases. Put simply, the energy spreads out and becomes less usable. Stars go supernova, black holes slowly evaporate, hot things cool down, and even cold things heat up. Entropy dictates how we define time. Generally, what we refer to as the future is just a state of higher entropy or more spread out energy, and a state characterized by lower entropy is what we call the past. So, the further back in time we look, the lower the entropy should be. We don't know why this is happening, but it's something pre-Bang hypotheses revolve around. Some physicists propose that the universe before the Big Bang was hibernating. According to the idea, it remained compact and still throughout an everlasting past. Then, at a particular moment, a trigger initiated a change. This pre-Bang universe is thought to have been metastable, only appearing stable, while being inherently delicate. In the scientific community, this state is also known as a false vacuum. To understand the concept, picture a landscape with a valley nestled between towering mountains. People within the valley might believe it's the most stable point, yet beyond the mountains lies a sheer drop to the sea, the true vacuum or an ultimate state of minimal energy. Similarly, the young universe could have existed in a state of false vacuum until a catalyst triggered a transition into a truly stable state. So, what was it that set the universe in motion? In the world of quantum mechanics, there's a lot of uncertainty in the way particles act. If the pre-Bang universe was governed by laws of quantum field theory, anything could have happened. Imagine an underground river running beneath the valley, slowly carrying away tiny pebbles into the sea. This continuous flow gradually weakens the valley's foundations until a critical point is reached and the valley caves in, and boom, This is how we believe the universe instantly expanded into what it is by the Big Bang. For a long time, the idea of a singular point containing all matter and energy was accepted. Today, modern physics suggests there was no such thing as a singularity. Instead, the phenomenon responsible for our universe's origin is cosmic inflation. It all started as a cold and empty space 100 billionth the size of a proton. Yet, it was brimming with so much energy, the pressure within produced a repulsive gravitational force. This force triggered an astounding expansion, where the universe doubled in size over 80 times before resulting in fiery Big Bang. Think of a bomb that's about to go off. First, the explosive material starts to break down, creating hot gases and releasing energy. As gases accumulate and spread out, they push against the walls of the bomb, creating pressure. Only then does the detonation take place. Similarly, all the energy used to fuel the universe's inflation was released into space in a bang, heating it and producing different particles. At that point, the universe is expanded to almost an octillion times its original size. Once focused and tightly packed energy became spread out throughout vast distances. However, entropy can also be interpreted as the tendency for all things to transition from a less likely state of order to a more possible state of chaos. But how can a seemingly organized universe we observe today, one filled with all the galaxy clusters and star systems, be more of a mess than the early soup of extremely hot particles? Imagine the Big Bang as a party popper. As you pull the string, it bursts into a dazzling display of confetti. We'd expect the confetti to scatter chaotically in all directions, forming a random assortment of colorful pieces. Yet what we see is the confetti organizing itself into perfectly shaped numbers and geometric objects, circles, squares, triangles, which represent subatomic particles, atoms, and molecules. And not just that, the universe appears to be uniform in all directions. Across its vast expanse, the universe has mysteriously consistent temperatures. Regardless of the direction researchers study, they measure a temperature of around 2.7 Kelvin throughout the cosmos. This is something that shouldn't happen, and here's why. Even though the age of the universe is an estimated 13.8 billion years, its observable expanse is much larger. Today we can peer as far as 46 billion light-years away from Earth in any direction. Together, this makes the diameter of the observable horizon 92 billion light-years. This is because space itself expands quicker than light. But particles that carry information, like photons, are limited to the speed of light. And so, how could 2 points in space that are separated by more than 14 billion years have the same average temperature if these distant regions of space haven't had enough time to exchange information yet? This is known as the horizon problem. Another puzzle is the flatness problem. Einstein's theory of relativity reveals that massive objects curve space-time, influencing the motion of matter within it. Locally, stars, galaxies, and black holes cause irregularities in this space-time fabric. But when observed on a larger scale, these irregularities average out, resulting in a smoother structure. This overall uniformity suggests that the universe is flat on a grand scale. So how could something like this happen? There's an idea that cosmic inflation never comes to a full stop. Instead, there's a high entropy mother universe, which continues to expand forever, only coming to a halt at specific regions. Wherever it does stop, new low entropy universes form isolated from one another. It's possible that these pocket universes are being created all the time in an endless sequence. The Big Bang fits well into this theory, but it doesn't mark the beginning of the universe as a whole, only a tiny part of it as a result of quantum fluctuations happening on a much, much grander scale. Although life as a whole persists, there's more of it with each passing moment. Let's look at it this way. Every pocket universe runs out of energy, cools down, and ceases to exist. But at the same time, more of them are being created. And because every possible universe will exist, life would too. and there would be even more of it with the creation of new pocket universes. If the concept of eternal inflation holds true, then an infinite number of universes has to exist, each characterized by its own distinctive array of natural constants. And so it's inevitable that there's a universe like ours, seemingly tailor-made for life, with stars producing crucial elements and everything working in harmony. Or maybe the explanation is much simpler, and it doesn't require the existence of multiple universes. The cosmic inflation theory has different variations. The model proposed by Alan Guth suggests that the expansion of the universe wasn't constant. In its earliest phase, the universe was so small that the regions of space that are now extremely far apart were still close enough to exchange material. Then, space doubled and redoubled in size over 80 times within a fraction of a second, before the pace of expansion decreased and continued in a more steady pattern. Even right now, the universe is quickly expanding. If scientists had a probe that could travel at the speed of light, and they sent it on a journey to explore space today, it would be able to cover just around a third of the observable horizon. This is about 3% of its total volume, meaning that about 97% of the visible universe is already beyond our reach. So, we can never be certain the cosmos is consistent throughout its entirety. The observable universe is just a splash of paint on a much larger cosmic canvas. Here, in our little corner, things might seem uniform, like the flatness of space and the overall temperature equilibrium. But, just like a wider view reveals the curvature of the Earth's surface, a broader cosmic view could expose variations we don't notice from our limited viewpoint. Before inflation, the universe might have had big temperature differences. As it expanded rapidly, some areas were pulled apart too far away to see, possibly concealing those variations from us. Or maybe inflation stretched the universe to an extent where it became flat. If the Earth was small enough to fit in your hand, it would feel as smooth as a perfectly round ball. Even Mount Everest would be too tiny to notice. Many scientists find the idea of eternal inflation frustrating. If each separate universe has different laws of physics, why study the behavior of particles and the laws shaping our universe? A more popular hypothesis is the cyclic universe, one that pops in and out of existence over and over again. Instead of perpetually expanding for an infinite duration, the universe in the bouncing cosmological model would experience different phases of inflation and contraction. Each cycle starts with a Big Bang, a monumental burst of energy that launches a fresh era of cosmic evolution. Galaxies, stars, and intricate structures emerge as the universe expands and matures. But as time flows, a mysterious force called dark energy steps into the spotlight. Its subtle influence gradually becomes dominant, pushing the universe to expand faster and faster. Dark energy's relentless push eventually overwhelms gravity's pull, leading to the Big Crunch, a dramatic implosion where everything collapses back into a searing point of origin. But this isn't the end. It's just the beginning of the next cycle. Another Big Bang rekindles the cosmic rhythm, repeating the process in an endless loop. Some physicists believe a significant contraction of space might not be necessary for the Big Crunch to occur. As the entirety of the universe shrinks, the observable horizon does so much faster, till it becomes a minuscule point. As the boundary beyond which events are hidden from view closes on us, we would see ever less of the cosmos. First, distant galaxies would vanish from our sight, followed by stars within the Milky Way. Then, even closer objects like Mars and the Moon. Gradually, it will reach a point where people wouldn't see things in their room. And then, even the people would start to disappear. This process continues until individual particles are left in isolated existence, cut off from interactions with their nearest surroundings. Everything becomes suspended, frozen in time and space. Structures and entities, once bustling with activity, lie dormant. This state persists until the cosmic horizon starts expanding again. If the universe undergoes an endless cycle of creation and destruction, it's only a matter of time till we go through another collapse. Whether something like this is possible or not depends on the overall curvature and density of our universe. If the fabric of space-time holds a significant quantity of energy and matter, this collective gravitational pull could make the universe positively curved, like a surface of a sphere. This curvature has a unique quality. It folds the canvas back onto itself, effectively slowing the universe's ongoing expansion. And this might go one step further, reversing the expansion of space altogether. Everything would collapse in a big crunch, where things once scattered across the vast cosmic expanse end up in a tiny fraction of space. But if the overall density of matter is sparse, then space-time might have a negative curvature similar to the form of a saddle. While gravity's gentle pull is present in such a universe, it would lack the strength to hold back the cosmic rapid expansion ignited by dark energy. In this case, the entirety of cosmic matter would spread out with an ever-increasing velocity, making the universe bigger and bigger indefinitely. The universe's ever-expanding nature lays the foundation for another intriguing hypothesis, one involving extra dimensions and based on string theory. It's called brane cosmology. Imagine all of existence as a giant cosmic book. Each page of the book exists in a lower dimension than the book itself. Scientists call these flat surfaces branes, and the idea is that they represent different universes, each doing its own thing based on a unique set of physical laws. These branes can move and bump into each other, and when they collide together, they produce a lot of heat and energy, leading to the Big Bang. Our current understanding tells us that the universe grows larger and cooler over time. This means that long ago, things were much hotter and denser. Although we may not know how, 13.8 billion years ago, the universe did begin. But what exactly was happening right after the Big Bang? Planck time and Planck length are the two fundamental units in physics. To understand these concepts, imagine a photon racing through space at the maximum speed possible, the speed of light. The photon is traveling a certain distance, a distance so short that it's the smallest length that has any meaning in the universe. The Planck time is the precise duration it would take for this speedy photon to traverse the smallest indivisible distance, also known as the Planck length. Both of these units represent a measurement at the boundary of what our current understanding of physics can describe. 100 million trillion trillionth of a second after the Big Bang is the period known as the Planck epoch, the furthest point in time that modern physics has been able to explore. Back then, the entirety of space was the size of a Planck length, quintillions of times smaller than a photon. This tiny speck of dust had a temperature of absolute heat, an opposite of absolute zero. Even 100 billion Kelvin within the core of a post-supernova neutron star pales in comparison to the magnitudes of the Planck temperature. Temperature serves as a reflection of a particle's motion, energy, and vibrational intensity. Essentially, the hotter it is, the more rapid the motion. Physicists believe this was the age of unpredictable quantum foam. Everything vibrated and changed randomly, giving rise to micro black holes and wormholes that would disappear as soon as they were created. In the very dawn of existence following the colossal burst of the Big Bang, the universe brimmed with a singular, all-encompassing force, a fusion of gravity, electromagnetism, weak nuclear force, and the strong nuclear force. The Grand Unification period spanned an astonishingly brief window, until about 10 to the negative 36th power seconds after the Big Bang, when the universe was still a seething cosmic furnace of energy. It is at this moment that scientists think the fundamental forces of nature started separating from each other. The first one was gravity, which emerged as a distinct entity, shaping the universe's future dynamics. The energy levels during this epoch were surging at a staggering 10 to the power of 28 electron volts. To put this into perspective, the universe was pulsating with 1 trillion times the energy achievable at our most advanced particle accelerator, the Large Hadron Collider. In a gradual cooling of the cosmos, the strong nuclear force finally broke free. Approximately 10 to the power of negative 12 seconds after the Big Bang, the electromagnetic and weak forces separated from each other. Soon, the Higgs field emerged, giving rise to the Higgs boson, a particle responsible for granting mass to other elementary particles like quarks and leptons. The universe's temperature at this point was around 10 to the power of 14 Kelvin, continuing to drop substantially. As particles interacted with the Higgs field, they acquired mass. This process, known as the Higgs mechanism, fundamentally shaped the future building blocks of matter. Somewhere along the way, baryogenesis, a crucial process in the early universe, occurred. Scientists don't know the exact timing, but this hypothetical event is believed to have taken place when temperatures were so incredibly high that the random movements of particles happened at relativistic speeds. As particles and antiparticles collided, they annihilated each other, and somehow matter dominated over antimatter. This asymmetry resulted in a slight excess of matter, with roughly 1 extra proton for every billion antimatter particles. The seemingly minor disparity set the stage for a matter-dominated universe, shaping the trajectory of the cosmos as we know it today. The fundamental constants and conditions appeared finely balanced. Roughly 1 microsecond after the Big Bang, temperatures cooled to around 10 to the power of 10 Kelvin, allowing quarks to form protons and neutrons. By the end of this period, the universe was roughly 1 second old. Around 3 minutes after the Big Bang, temperatures plummeted to 1 billion Kelvin and below, allowing for nucleosynthesis. During this brief period, light atomic nuclei like hydrogen and helium were formed in abundance. Protons and neutrons combined to create these nuclei, setting the stage for future stellar processes that would produce heavier elements and pave the way for the formation of planets, stars, and galaxies. Roughly 380,000 years after the Big Bang, temperatures had cooled to around 3000 Kelvin. The very first molecule was formed of helium hydride. This marked the transition from purely atomic matter to molecular complexity. The binding of helium and hydrogen ushered in a new era of chemical interactions, preparing the cosmos for the emergence of more complex molecules and structures. With electrons now bound to nuclei, photons were free to traverse the universe without any obstacles. The emergence of neutral hydrogen and helium atoms allowed the first light to penetrate the cosmos, illuminating its history. The universe became transparent, allowing future human civilization to trace back time to this epoch. In the subsequent billions of years, the universe evolved. Dark matter, a form of matter that doesn't emit light, presented its gravitational influence. Physicists believe that dark matter outweighs ordinary matter by a factor of 6 to 1. Dark energy, an equally mysterious force, began to dominate the universe's expansion around 5 to 6 billion years ago. Up to this date, the nature of these forces remains elusive, waiting to be unveiled. Understanding the past helps us glimpse the future, but what fate awaits our universe? As we stand on the threshold of time, these cosmic mysteries beckon us to explore the unknown chapters that lie ahead. Will the universe gently fade into a heat death, or will the mysterious forces of dark energy lead to a dramatic big rip, tearing everything apart? Let us know what you think in the comments, and thanks for watching.